In this lecture, we're going to start looking at earthquakes, how we deal with them, and other non-linear motions that may be problematic in your analysis of your data. So the overall scope of what we're going to look at is in previous lectures, we've shown common time series models, which are linear rates of change, seasonal terms, potentially correlated temporally correlated noise in your data. But there's other perturbations that can happen. You can have discontinuities due to equipment or environmental changes, discontinuities due to earthquakes, which you have no control over, and then non-linear motions after earthquakes, and then other non-linear transient effects, such as volcanic inflation events, etc. And what we're going to look at is some of these phenomena. It's the who's of this type of deformation, and then some of the recommendations of how you implement and handle these things in your gamut K processing. So equipment changes, this is a main concern for antennas, although receivers changes can also sometimes have impacts on your changes. And what we've found that even antennas of the same model, we end up having changes in positions which are not acceptable large amounts. This is an example of a site where this particular antenna was switched for exactly the same model and type, and yet after the switch of the antenna, the position changed. In the gauge NOTA network, we find that very common even for large choke ring antennas, that the phase center location for a particular antenna is not necessarily where the manufacturer, where it's been calibrated to be. We have a program, STIMF to rename, that's very useful creating these automatic lists. So your station.info file contains the information of what antenna exists at a station, and what you're able to do is to use STIMF to rename to be able to take that information and write it into an earthquake file for Globe K. So you can also get changes that happen during the changes of the multipath environment. This is a couple of examples of stations where somewhere buried underneath this rock and all this vegetation is a GNSS site. And these are the 4 positions. And then there was the major fires in California at the time, and all of the vegetation around these particular sites, and this site buried in here, all disappeared after the fire happened. When we look at the time series for these sites, there are various other events occurring, earthquakes and equipment changes. But here, this little green line, where in the height in particular, you see this slight discontinuity, that is the consequence of the removal of the vegetation around this site. And again, you'll see this site is relatively close to the ground. And as a result, the vegetation can have large impacts with the long temporal wavelengths, which means the position can change when that environment changes. So when you have this type of thing happening, in Globe K there is a rename scheme. And we basically keep the first 4 characters of the name the same, and then it's the last 3 characters which change. And so for the standard processing, when we change antennas, for example, or equipment changes, we go from a GPS site to a 2PS site to a 3PS site, etc., as we go forward. And then if you go above 9, the 10th letter, we then jump to J and continue up with J, K, etc., until we run level Z, and at which point we're in trouble because we can't go any higher than that with this type of scheme. So far, we've not run out of options for these sites. So these for automatic changes, typically, we have a shell script that does that. That's what happens in STIMF to rename. For manual renames, where you may have seen something such as that fire, where there is no particular event in station.info, you can do a manual rename. And for those, we tend to use letters A, B, C, etc. But remember, G is that special case, and you should not do it. Now, when we do earthquakes, it's the last 2 characters that actually change associated with the earthquakes. So earthquakes are very common. We fortunately have them. They occur at known times. Any earthquake that would be affecting a GPS station will be detected by seismometers, etc. You typically see a discontinuity associated with the earthquake. One little warning you have to be careful of is even in a case like this where there's a large displacement of the site due to the earthquake, the day of the earthquake, if it is processed in the normal fashion, it will generate a coordinate estimate and with a reasonably small uncertainty. So even if you're having a large displacement, if the earthquake occurred at 1200 hours UTC, the point that you estimate would actually fall pretty much midway through this day. If it was early in the day, the point would be closer to this one, and if it was late in the day, it would be closer to the one at the end here. So be very cautious that if you see this little blip in a time series and then an earthquake, it's typically not a pre-seismic motion, it's simply the averaging across the co-seismic event in that day. If you're really careful in doing processing, then in SH gamut, you can set the epoch range of your processing so that you have processing up to a minute or so before the earthquake, and then processing starting, say, 5 minutes after the earthquake. So you would split this day into the two parts. When you do that, you typically see this very rapid offset due to the earthquake. So far, we've never seen a pre-seismic signal prior to an earthquake as we go through. Now, of course, you notice here that this earthquake also tends not to have just caused an offset. There clearly is a post-seismic deformation term happening in here. And for this particular station and the Omayakukupa earthquake, it's not obvious, even multiple years after the earthquake, that this velocity is still the same as the velocity before the earthquake. And this is one of the things we're seeing with earthquakes, is that potentially some of them do have changes in the coupling on the faults after the earthquake, which means there may well be a secular velocity. It could also be that this is simply a logarithmic term, and we'll talk about that in a little bit as we go through. So how big an influence do earthquakes have? Well, this is a calculation based on different types of earthquakes of different magnitudes. And the bar and risk curves here show you the medians and then the outlier points as to how far a distance away does an earthquake affect your sites. And so you'll see for a magnitude 7.5 earthquake, for example, it's often 1,000 kilometers. But for a magnitude 7, it's a few hundred kilometers. And these are not that common. Magnitude 6s are still quite a small influence, and magnitude 5s, etc., it can be quite a small influence of distance. So in the earthquake def line, which goes into an EQ file, which is read into globe K, we denote that earthquake by changing the last two digits, the last two characters of the file name. And we have a coding scheme we use. Some earthquakes, we actually have a name for them, and so we make a two-character representation for them, HT for the hectomine earthquake, etc. For the gauge processing in NOTA, we these days just use a numeric value for most of the earthquake, unless it's so well known that we assign a two-character code to the earthquake. There is a shell script that automatically reads earthquake catalogs and a list of sites that you are processing, and it will make the earthquake definition file for you. You do need to check it because it will be conservative, particularly for these smaller magnitude earthquakes. It will assume that you may have a co-seismic offset, but when you look at the time series, you often find that it's not. This is particularly the case for small earthquakes, which happen to be, appear to be very close to your site as you go through. So what happens after the earthquakes? Well, there's a couple of different models. Logarithmic decay is something which is nominally predicted by rate and state friction. And it has a long decay time. The velocity perturbations reduce simply as one on time. It does not depend on the time constant on the logarithmic term at all after you've gone a small amount away from the time constant. And so this means that if you have logarithmic decay, there can be a very long time interval until the velocity returns to normal. Some of the earthquakes we've looked at, we have logarithmic amplitudes of 10 to 15 millimeters. A 10 to 15 millimeter logarithmic term means that 10 to 15 years after your earthquake, your velocity is still not within 1 millimeter per year of what it had been before the earthquake. The other model you see is exponential decay. And this is the one where the velocity decays out and it relaxes and your velocity after a certain number of e-folding times will be back to your original value you see. Both of these models seem to be appropriate. When we use programs like TS-FIT, we're able to estimate both types of motions, and experience suggests that for some earthquakes, both types of motions are needed. In the ITRF 2014 system, both types of motions are included, and for some earthquakes, multiple terms are included for those motions, trying to have a parametric model which represents that post-seismic deformation after the earthquake. Just to give you an example of how these look and the complexity of doing this, this is one particular earthquake, a particular site, and in the left-hand frame here, we're estimating a logarithmic decay after the earthquake. The red line is the time of the earthquake. And you'll notice in the east coordinate, that seems to do quite a good job in representing the logarithmic decay. But in the north component, there clearly is something else happening within the first few months after the earthquake that's not well represented. In the exponential decay case, we'll see in the north component that that actually seems to work quite well. And in both cases, you'll notice that there's this rather large, long-term systematic in the background of this time series. That type of motion is not well understood as to what that represents. Statistically, it clearly is something that is affecting the site. The correlated noise models that we use try to capture the impact of this on estimating a secular velocity for this term. And that's what it's trying to tell you, is that when you estimate a secular velocity, what is the impact of the other non-white noise terms that are affecting your time series? Now, the exponential decay worked well in the north, but in the east component, it does not work well, whereas the logarithmic did. So this site clearly is one in which both types of models are needed. And this is something where you have to look at individual earthquakes. In the future, we may end up with a time where earthquake post-seismic models are sufficiently good that we could actually have a prediction based on a numerical solution of the finite element equations as to how things should be moving in a viscoelastic earth. We are nowhere near that point at this point for understanding post-seismic. So nearly everything we do is these parametric levels of models to try to account for the variations due to earthquakes afterwards. Very active area of scientific research at the moment. Of course, you can also have many earthquakes, and you can have complexities that arise from this particularly inactive areas. The most rapid sequence recently has been the Ridgecrest earthquakes from July of last year, where we had one earthquake, and then within about 36 hours later, or 40 hours later, there was a second much larger earthquake. In that particular case, we ended up with just 1 day of data, full 24-hour session of data between the two earthquakes. And so it may be that you have to rapidly apply these earthquakes as we go through. Most times the large aftershocks of earthquakes don't produce significant motions, except for maybe a few sites very close to where those happen to occur. So we have this renaming as we go across, and also to represent these post-seismic deformation types of models, then we have the extended records in the GlobeK APR files that can be used. And those extended records can have logs and exponential terms as needed. And in this particular case, again, with this P49 station, you'll see we have a velocity like this. And then in that intermediate period between the two earthquakes, the velocity certainly appears to be linear and going in a completely different direction. And then after the second earthquake, the velocity may or may not be the same as it was before. This is where careful analysis is needed to understand what is actually happening. However, sometimes in earthquakes, things are not as clean as one would like. And this is an example of a site P49, which is part of the NOTA network. Again, this is the 2010 Almayad-Kukupar earthquake, clearly a co-seismic offset. We saw before that there was rapid post-seismic deformation. This particular station looks like it was more exponential and quite rapid. But then in the east component, it has this strange characteristic. And then this change, rapid change at this particular question mark here. And what was noticed about this particular site was that it had been under maintenance just before the earthquake, and a metal washer was left on top of the choke ring antenna underneath the radar. So it was not obvious that it was there. That did not seem to affect things very much before the earthquake. They think because the washer was sitting right on the very top of the little gray Dorn-Margolan elements and did not have a great impact. But then after the earthquake, it was shaken loose. And at that point, it became on the side. What's still not known to this day is why it tended to produce a signature that looked like the station was moving. The arrow is where a maintenance worker took the radome off, realized the washer was there, and removed the washer. Now, of course, in the complexity of all of this, what's interesting is that in the height, that did not seem to have much of an effect. And we have this rather large height offset. And then also the velocity and height may be different after this earthquake. Again, not completely obvious. And then we'll see in height there's a jump at this point, which may or may not be another unknown event, or it could be an antenna change. It does, again, that's something which, as you look at time series, you have to go and evaluate. So there's lots of other types of events that can affect your sites, and they can be motions of the monuments, often non-tectonic in origin. There can be propagation medium effects, which we'll talk about, and there can be failed equipment. So with continuous sites, the data can be analyzed through some of the diagnostic variations you see. You have an example of what the time series looks like, and you can tell when the time series looks different than it did before, and use that as a guide to go and look at things. If you're dealing survey mode data, that's more difficult to do, and so we often would like to rely on other things. And from the continuous data, we often look at things like the multipath measurement at the site, which is something derived, affects the shooter range, and it's derived from a comparison of shooter range with phase data. And often we see that when there's a problem, the multipath characteristics of the site change. Signal to noise ratio is also a very good measure because the signal to noise ratio is essentially orthogonal to the phase measurement. So if something is affecting the phase measurements, the orthogonal component often also shows up in the signal to noise ratio. And as a result, changes in signal to noise characteristics of a station can be very strong indicators that something has changed at their sites. So I'll run through somewhat of a rogues gallery at the moment of things that can go wrong. And again, these are based on results from the Network of Americas, the continuous sites that are running. This is a site P320, which is sitting in this area in part of the geothermal field in California. And this particular continuous station, as it comes through, we'll notice at the green line, we seem to see a change in the northeast velocity of the site and possibly a change in the height. Now, in trying to analyze this motion, what we see is we see northwest motion, some minor subsidence. And then if we take those, and then if we look at what happens in here, this is where they started to do a injection into the geothermal field to try to enhance the recovery of geothermal energy out of the field. And if we detrend the time series based on the data before that injection happened, then what we clearly see is there's this change in the velocity associated with that generation injection going on. So this is a human-induced change in the site. And unfortunately here we have enough records of what was happening, enough knowledge about the station to know where this was happening. And then we see that westward increase in motion. There's some which are much more bizarre and sometimes are actually quite geophysical. This is from Bombay Beach, which is in Southern California near the Mexico border. And here is an area where they have earthquake swarms. It's part of where the ridge system enters into the San Andreas fault system. And so you see all these large creep events happening. The red line here is the Omayakupa earthquake. But again, you see other events. You can see these events aren't rapid. They actually can be relatively slow type events. And so, again, we're not fully sure of exactly what's causing all of this. But again, the magnitudes, tens of millimeters of variation going on. And understanding these, this is what you are trying to achieve in doing your GNSS processing. Interestingly, you also see these occasional outlier data points here. We do know from processing that this type of outlier is seen in both gamut and gypsy processing. Sometimes the magnitude's a little different, particularly if it's an artifact. So again, these are things that you can spend a lot of time exploring and understanding. This might be one where you would just want to exclude that data point necessarily. Although again, with continuous data, having a few outlier data points generally doesn't affect your results very much. We can also look at more volcanically active areas, such as the Yellowstone caldera region. And what we've done here is we've taken the sites around Yellowstone and we've essentially profiled across the Yellowstone caldera. And what you see here is the deformation occurring as we go across the caldera. And this is along the profile, across the profile, and this is in height. And we clearly see these large outlier points here in the height system. And these, you'll notice, have very large error bars on them. And this is something being generated from the correlated noise model that we use. And if we look at the time series for the sites in this group, we can see precisely why that is happening. So here you see time going in. The different colors are different stations. They're listed up here. And again, you'll see that the error bars on the individual data points are all staying very consistent. And that's because this is not occurring due to noise in the instrumentation or anything. This is, in fact, the effects of deformation occurring in the network. Very non-linear, non-steady type deformation happening. These data points out here with the large error bars, those are ones where something has gone wrong. Presumably there's very little data on these days, and so they have large uncertainties associated. This is what you would like your error bars to be reflecting, that when you do have noisy data, the error bar reflects it. But this clearly is actual motion of the stations at this point. We also have episodic tremor and slip. And this is an example from Cascadia. And this is a phenomenon which has now been known about for quite a long time. And you clearly see the sawtooth behavior. In the height here, you'll notice the red line is an annual signal that's being fit to the data. And this is what I was saying in the previous lectures on reference frames, that this strong type of height signal, this is something we see across the whole northern hemisphere and is certainly believed to be associated with ice and water loading during the winter months of the year. You'll notice that the site in the beginning and the New Year points is all low when there's a lot of loading on the surface and pushing the whole northern hemisphere down. If you look carefully at this curve, which also has an annual superimposed, you can see the times at which these rapid decreases occur is different from the annual period, and it actually has something like a 14-month period as you go through. So when you're looking at sites and you're understanding what sorts of examples are out there, certainly if you're looking at the UNAFCO Gauge NOTA network, we do have technical data news that you can find in Google+, which gives reports on various aspects of it. The Gauge Analysis Center generates quarterly reports, which often contain information about anomalies that have been observed. We'll give you some rogues gallery here, just to give you an idea of some of the things that can go wrong. This was a site that was installed. This is actually a seismic site, and there is the GPS antenna sitting onto the mount where the solar panels are being arranged. Well, it turned out that they did not generate this vault very well. They didn't dig the vault very well, and the vault actually collapsed around the edges, as you can see in this photograph. And when it collapsed, it actually tilted this whole thing in closer. And so you can see that there's this rapid collapse and then variation going on in the north and the east components of the site associated with that. And then what appears to be some subsidence of the site as well as we go through. So this is poor. Again, this is a case where you go in and you try to investigate precisely what happened at your station. We also have sites that are prone to landslides. This again is P229. And what's known is that this piece of the site is sitting about here. This piece of land in the past has collapsed and had landslides on it. And we can see that as this region has water come and go out of it during the summers and the winters, that we see an oscillation in the time series. If we detrend these horizontal components, we see this large amplitude for a while, and then we get drought conditions where the amount of water affecting this site has reduced during the winter and the summer months. And as a result, we see more of a secular trend. So water is an issue. It can cause soil expansion, as in this particular case. It can also do things like loading. This is site P271. This is very strongly affected by groundwater. And you can see the small lake in the background here. This gets various sizes. The lake level in here can change dramatically. The site's right next to the lake. And if we look at the height in this site, we see that it oscillates with the seasonal annual variation. But then as the lake water starts changing dramatically, we see this large up and down variation in the height. These are large amounts, 120 millimeters. And this is the change in water level on the blue scale, which is at an order of 20 or 30 feet of water change in the wells nearby. This site also has strong periodic signals in the horizontal components, and that's because we're close to a large change in the mass, and that causes the site to push in and out as that water comes and goes, as well as go up and down. We can also have cases with vegetation, and this is an example where we have different pictures of this site at various points when it was first installed, a little bit after the tree had been allowed to grow, and then after the tree had been cut back, and then this is the point at which you'll see that we have outliers in one component due to the tree being nominally on one side of the site, and then the period at which it drops. This is actually an earlier incident where the tree was trimmed prior to this point. This site was continually had this problem. And you'll notice this is mostly in the east, which is where that site is, where the tree is relative to the site. There's also height variations, and you can see just before it's cut down that you can see the height has degraded in quality, etc. And the north is less affected. So this is due to vegetation, but not all motions you see are due to things actually physically happening outside of the antenna. This is a series of sites that have had bad antennas. And if we focus first on the blue site, which is the LTUT site, you'll see from the time it was installed, it had this very large north up and down motion, which might well have been a physical signal associated with water nearby, except that the location of the site suggested that did not happen. And then it also had sort of a vertical signal, but then the antenna was switched and the behavior became very, very linear again. The brown site is a case where the site was okay. This is actually a real earthquake displacement, some post-seismic potentially deformation going on. And then it also has strange behavior until its antenna is switched and it goes away. Again, most of the time, these types of variations, you can see them in things like the signal to noise ratio if you really want to isolate out the effect without necessarily looking at the time series to see how those are varying with time. Snow on the antenna is another thing we worry about for some sites which are at high altitude. This is an example of AB12. And again, you can see that there are periods of data here which look linear and look fairly consistent, but in between them is a lot of action, a lot of things happening in the time series, varying year to year. And this is all snow and ice buildup on the antennas. And when it melts in the summer, it goes away. We have some sites where it basically never melts and there's very, very little high quality data. Other sites where there's mostly a lot of high quality data, and then we just see some short periods of time at which things are outlier. So the final one is skewed residuals in atmospheric delays. This is a phenomenon we see increasingly, and we still do not know how to fully detect this in the data analysis in terms of error models or how to try to correct for it. But what you see in this particular case is that the north position time series, you'll notice that you see many residuals which are on the southern side negative. You see very, very few which are on the positive side. So this is an asymmetric outlier criterion. When we've looked at these types of sites, we often find they are near mountain ranges and that the impact seems to be parallel to the direction in which the mountain ranges are running. We believe that it's related to lee waves forming over the mountain waves. And because of the way lee waves form, it only occurs in one direction. And so this is dominantly by the wind direction that we see it in this particular direction. In theory, when we look in detail at these, we do see that the RMS scatter of the phase residuals is larger on these outlier days. And if you look carefully, the actual error bars are bigger on these days than they are on the quote non-affected days, but the increase is not nearly enough to represent the amount of station position deformation that we have. So recommendations with handling these types of things is really want to know what your goals are doing. You only want to fit for nuisance terms that you want to get rid of. You don't want to try to model everything out of your signal because sometimes they are things that are interesting, such as the seasonal terms that we've been looking at. And so again, depending on your goal, you may well just need to abandon data. That's more likely to do more harm than good. And we have this renaming scheme where you can rename to XPS, which is exclude the data point on time series and velocity field estimation, but the data point remains present on the single day points. It's not used in the solution, but you see the value on that day, or the XCL solution in which it is completely excluding all types of analyses as you go across. So you can add large process noise to a site to sort of have it have little impact on the results around it. Just be careful not to make it too large because of numerical issues. And finally, if you have single data points, you can downweight individual points with the sig northeast up command just to keep the data point in your time series so you can see it, but it has a large error bar so it does not affect any of the types of conclusions you're trying to draw from that data. This is a very varied area of research and one which there's a lot of active work happening. So in discussions, we can find more things to talk about. Thank you.